Algebra. Yesterday when you watched lesson 17, I said it was the second day of analyzing residuals. Well, I was wrong. Today is the second day of analyzing residuals. All right, get into it. So the previous lesson shows that when data is fitted to a line, a scatter plot with a curved pattern produces a residual plot that shows a clear pattern. You also saw that when a line is fit, a scatter plot where the points show a straight line pattern results in a residual plot where the points are randomly scattered. So today we're going to analyze what a scatter plot looks like and how I can compare it to a residual plot. So example 1 has 3 graphs. I could fit one on this page and 2 on the next page. For a scatter plot that has a pretty nice line fit in it, I mean, that is linear and it looks pretty good. I've got a few crazy ones. My residual plot, okay, we have a pattern. We're going to talk about that pattern after we look at these 3. Okay, this scatter plot, if I fit a line through here, this looks a little dippy. Good word, huh? But now I look at my scatter plot is even crazier. I mean, it's still linear, but sort of looks like the U.S. with Florida, Maine. Here I've got another scatter plot, and this one is crazy. Okay, so let's analyze why these are the way they are. So what does it mean when there is a curved pattern in the residual plot? So curved pattern in the residual plot. Okay, think about it for a second. I've got a curved pattern in the residual plot, and that would indicate that the relationship would be better described by a nonlinear function. Let's say better described nonlinear function. So I've got a curved pattern in the residual plot, and that would indicate that the relationship is better described by a nonlinear function, right? Okay, let's look at the next few and see if we can compare. What does it mean when the points in the residual plot appear to be scattered at random with no visible pattern? So now I've got a random one. And if we go back and look, that was the third graph. So this would indicate that the relationship is approximately linear. I mean, these are all approximations. It is crazy to think that if my residual plot has a scattered at random, then my scatter plot would be linear. But it makes sense that my residual plot is scattered around the horizontal line at 0. You know, if this is my residual plot, I'm plotting these because they're hovered around the scatter plot pretty tight. Okay, so if you have a random residual plot, your scatter plot is a linear relationship. So why not just look at the scatter plot of the original data? Why was the residual plot necessary? The next example answers these questions. So here, the temperature in degrees Fahrenheit was measured at various altitudes in thousands of feet above Los Angeles. The scatter plot below seems to show a linear, straight line relationship between these two quantities. It appears to be linear. Okay, I could put a line in there. That's not a line, but you get what I'm saying. So let's look at the residual plot. The residual plot is curved. So there's a clear curve in the residual plot. So what appeared to be a linear relationship in the original scatter plot was in fact a non-linear relationship. How did this residual plot result from the original scatter plot? Well, the residuals if I could spell, are the vertical, they're called deviations. From the least squares line, or the best fit line. Okay, I'm going to finish up here. So tiny little deviations again, if I could spell, deviations can be shown as much larger distances from the zero line in the residual plot. So if a very subtle curvature in the original relationship can be seen more clearly in the residual, therefore a very subtle curvature in the original relationship can be seen more clearly in the residual plot. That's why we draw a residual plot. So something that's really, really tiny or very subtle shows up in the residual plot as a curve. Okay? And there's one up there that I covered over. All right, volume and temperature. Let's try this. We're going to work on drawing some plots. So get your calculators out, please. If you could work along with me and practice, that'd be fantastic. Water expands as it heats. Researchers measured the volume in milliliters of water at various temperatures. The results are shown below. First thing we're going to do is construct a scatter plot of the data using your graphing calculator. I put list 1, list 2, went ahead and did the stat, calc, linear regression, stored it into Y1, zoom stat number 9, and got my graph. Okay, that's my least squares line and the scatter plot, which you would draw right here, right? So using the calculator, construct a residual plot. So I turned on plot 2, did my scatter plot. X is list 1, Y is your residuals. And this is my residual plot. It looks like a U. Even though that scatter plot was so linear, like amazingly linear, this one looks like a U, so what's that say? There's a clear curve in the residual plot. This indicates nonlinear relationship. Okay, crazy, right? And that's it. After fitting a line, the residual plot can be constructed using a graphing calculator. Check. A curve or pattern in the residual plot indicates a nonlinear relationship in the original data set. And then a random scatter of plots is a good thing that indicates linear. Cool? Cool. Good job today.